This conference will now be recorded.
All right, this is part 2 of the exam 2A review, and we are looking at number 15 now. So we're trying to do and find and simplify the difference quotient, which is this right here. This is two function evaluations. One is where you plug in a binomial of x plus h into the function. The other one is when you make everything in f of x negative, essentially. So I like to do these by working it out as kind of scratch work. So I'm going to work out f of x plus h, which means anywhere that we had an x before, because that's what f of x had before was a function in terms of x, we're going to kind of think of that as being a blank space right now. So kind of just copy it as if all the x's are gone. Inside each of those, you're going to put the new binomial x plus h. So now this has to be FOILed because it's a binomial squared. So that's going to be x plus h times x plus h. This we can go ahead and distribute. That's going to be 6x plus 6h. So this is going to be 3, and then we FOIL this out. So that's going to be x squared plus xh plus another xh. So that's plus 2xh's plus h squared. And the final step on that one is to actually distribute that 3 in front. So that's going to be 3x squared plus 6xh plus 3h squared plus 6x plus 6h. None of those are like terms, so we go ahead and do the second evaluation, which is a negative f of x. That just means -1 times your function. So that makes this negative 3x squared and negative 6x. So that's a lot easier than the other one. So now you take these two pieces. Those are your evaluations, and those become your numerator up here in this formula. So that's 3x squared plus 6xh plus 3h squared plus 6x plus 6h minus 3x squared minus 6x all over h. So that's what the difference quotient is in the formula. So then if we combine any like terms, we notice that the x squareds are going to be the same but opposite signs, so they cancel out. So is the 6x and the negative 6x. So that leaves me with 6xh plus 3h squared plus 6h all over h. You'll notice that everything on top has an h, so we can pull it out to the front. Pull out one of the h's. And then that cancels with the h on the bottom, so my final answer is 6x plus 3h plus 6. And again, if you're going on to calculus, this is a very important formula, and it leads us to talking about derivatives eventually. So it's a really good algebra skill because it just has you do some evaluations of functions, but it is useful later on. So 16 is the same kind of problem, except it's a little bit more involved. There's a little bit more on the examples. Hang on just one second. My document's not wanting to load the next problem. Let me scroll down even slower. There we go. So we're doing g of x plus h, which again, write this as if the x's are missing. So that's 4 blank squared minus 3 times blank plus 2. Fill in x plus h for each of the blanks. This is 4 times x squared plus 2xh plus h squared. We just did that guy. Remember, it's x plus h times x plus h. That's what that is. And then this would be negative 3x minus 3h. Bring down the plus 2. Distribute the 4 to everything in that trinomial. Bring down all the other pieces. So notice, again, no like terms to add together. Negative g of x is just -1 times the function. So that would be negative 4x squared plus 3x minus 2. And then we write all of those answers. Remember, this and this are both now my numerator. So this is the answer for the first part. This is the answer for the second part. So this is 4x squared plus 8xh plus 4h squared minus 3x minus 3h plus 2 minus 4x squared plus 3x minus 2 all over h. Okay, so then this would have the x squareds are canceling again. So are the 3x's, and so are the positive 2's. Notice everything that's left on top has an h in it. And then we would pull the h that they have in common out. Reduce that down. So this has an answer of 8x plus 4h minus 3. Okay, let's move on to number 17. 17 and 18 are both about writing transformations of functions based on a description that's given to you. So you kind of have to understand where the pieces go. And this first one is the parent function is y equals x squared. So when we look at a transformation, anything that happens in the x direction essentially or related to x is inside the function, so inside the squared part, and it's usually opposite of what you would think. Anything that happens to the y term, like moving up or down, reflecting over the x-axis because that changes your y value, those are usually outside of the function and they're exactly what you think. So when we talk about shifting right to, that's changing the x value. So that means that inside our new function here, think about that squared being there, we're saying that x is going to the right 2. So we're centering ourselves kind of the opposite direction. So that's actually a minus 2. And you can check this real quick. If you put 2 into there, 2 minus 2 is 0. So it kind of takes you back to a center of 0. Reflecting about the x-axis, that means we're changing our y value. And remember, a reflection is always a negative sign attached somewhere, either inside the parentheses or outside. If it's an x-axis reflection, it's outside. If it's a y-axis reflection, it's inside. So this is outside. And then shift the whole graph down 4, which is also changing the y value. And that takes us as exactly what we think. It's a minus 4 at the end. So there is the function. Now there's a lot more going on, but this is kind of just a summary since you've already learned this material. All right, so let's do this one. Find the equation. Now this time our parent function is the square root of x instead of x squared. So reflecting about the y-axis, that means we have a negative inside with our x. Okay, because we're reflecting about your y-axis actually changes your x value. Stretch vertically by a factor of 2. So that's changing our y value, so it's outside, and outside is exactly what you think. So we times this whole thing by 2. Then we shift the whole thing up 5. So that's a vertical shift, which is added or subtracted at the end. So there is that one. Now 19, the next 6 problems are actually where we graph the transformations. So to graph a transformation, you have to first understand the shape of the parent function and then know your transformations. So this is absolute value of x because that's the parent function we're comparing this to. So if you think about absolute value of x, if you do the absolute value of 0, that's 0. Absolute value of 1 is 1. Absolute value of negative 1 is also positive 1. We learned that absolute value is a V shape. Okay, and these are our 3 main points. This right here says that we need to take those. See, this is added or subtracted after the absolute value. So this is shifting us either up or down. And when it's outside the actual function, it's exactly what you think. So that's going to be down 3. So you're literally going to just take those points. So this is not our final answer. This is going to be our answer. And we're going to shift every point down 3 on the graph. So at 0, 0, we go down 1, 2, 3. We were at 1, 1, we go down 1, 2, 3. We were at negative 1, 1, we go down 1, 2, 3. So this is our final graph. Now that was a 1 transformation. The second one here is still absolute value of x, but it's got 2 transformations. This is saying to go down 5, but this is inside the function, so it's opposite of what you think, and it's affecting x, so it's either right or left. So since I see a plus 2, it's actually opposite direction in my head, so it's left 2. And think about that. Negative 2 centers that out at 0, so that makes sense. So we still take that same plot of absolute value of x, which was 0, 0, 1, 1, and negative 1, 1. That's the general shape of absolute value of x. And I'm going to do this from the inside closest to x out. So that's how you work out transformations. So this is the first transformation because it's inside the function and closest to x. This is the second transformation. So my first graph here is just shifting everything to the left too. So it's not got the -5 yet. So I take each point, so 0, 0, and go 1, 2. -1, 1, go 1, 2. 1, 1, go 1, 2. So 2 to the left. So that's not my final answer. And then I want to take that specific location and I want to shift everything down 5. So I might need to graph this a little higher. 1, 2, 3. So we were at -2, 0. So we want to go down 1, 2, 3, 4, 5. We're at the point 1 or -1, 1. We want to go down 1, 2, 3, 4, 5. And we're at the point -3, 1. And we want to go down 1, 2, 3, 4, 5. So notice each transformation just builds upon the one before, and we've finished all of the transformations. Now, obviously on your test, you'll have nice gridded paper, but we're kind of just rough sketching it here. So this guy is squared. So remember, x squared is kind of the parent function there. And we know that x squared has a u shape. 0, it actually has the same starting 3 points as the absolute value. What happens is that as you grow farther out from 0, you get more, you grow quicker than you do in a straight line. Absolute values grow kind of at the same slope in both directions. So here we're curving. So again, this is a shift to the right 1. Since it has that happening inside, we do opposite of what we see. And so we just take our graph, and this is just one transformation. So we're going to move everything right 1. So here's 0, 0, move it right 1. Here was the point 1, 1, move it right 1. Here was the point -1, 1, move it right 1. And then we keep our shape of our parabola, the U shape. So there's that graph. Now this one has 2 transformations going on. It has a negative in front of our x squared, which means we flip the graph upside down over the x-axis. So this is reflect x over x-axis. And then this is after the squaring part. So this is shifting down 2. Again, you want to do these as an order of operations. This is closer to x because we would multiply before we subtract. So this is going to be done reflection first and then down 2. So let's draw our parent of just x squared again. U-shaped graph. Negative x squared takes the whole graph and flips it upside down over the x-axis. So 0, 0 doesn't change since it's on the x-axis. And then negative x squared minus 2 means we shift each of those new 3 points down 2. So here was 0, 0, so we go down 1, 2. 1, -1, we go down 2. -1, -1, we go down 2. So notice it's still u, but it's upside down and down 2. And that would be the final placement of that one. All right, so that takes us to the last group of these, which is the square root of x ones. There are other parents out there. There's a cubed root of x and there is a cubed. They're just not the ones we put on the review. So this is knowing the parent here. Now I would say this is the hardest one because this one does not have anything on the left side of the y-axis. And that's because in a standard square root of x, x has to stay greater than or equal to 0 or you're imaginary. So if you plug in 0, square root of 0 is 0. If you plug in 1, square root of 1 is 1. You don't want to plug in 2 or 3 because those are not perfect squares. I plug in 4 because square root of 4 is 2. So what you get for square root of x is kind of half of a parabola on its side. So then this is shifting this left 4, and that is up 3. So we're going to do this in pieces. So the absolute value of x plus 4 needs to shift the graph that we had currently left 4. That's the only time you get anything on the left side of this is if you're shifting it. So 1, 2, 3, 4. So that's the new point for the start. 1, 1 is going to go back 4 as well. So 1, 2, 3, 4. And 4, 2 is going to go back 4. So 1, 2, 3, 4. So now it's on that y-axis. So that's my first step. Then I want to shift the whole graph up 3. Okay, so then I take that point 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So this was at -4, 0, so it goes up 1, 2, 3, so it's kind of floating now. This was at the point -3, 1, so it's going to go up 1, 2, 3. And this was at the point 0, 2, so it's going to go up 1, 2. I think I went too high on that middle point. Let me redo that one. Okay, we were at 3, yes, 1, so that's 1, 2, 3. There we go. And then at 0, 2, we go up 1, 2, 3. So you still get your same shape, it's just been shifted. Okay, let's do this one. This one actually has 3 transformations. It has a shift to the right inside. So this is going to be right 5. This is a reflect over the x-axis. And this is then up 1. So in terms of order of operations, the one that's inside the radical needs to be done first. Then we would multiply by a negative before we would add. So that's going to be the order that we do them in. So again, we have our square root of x, 0, 0, 1, 1, 4, 2. Those are the 3 standard points you start with. And we're going to start off with that x minus 5 under the radical. So we're going to shift the whole thing right 5. Okay. So 0, 0 is going to move to 5, 0. 1, 1 is going to move to 6, 1. And 4, 2 is going to move to 9, 2. So there's step 1. Then we reflect it over the x-axis. That puts the negative in front of it. That just flips us upside down over the x-axis. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. So we're going to be upside down. So 5, 0, 6, -1, and 9, -2, like this. And then we want to move everything in our graph up 1. Sorry, my square root looks kind of funny there. So we take those points and we're going to shift them all up 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 5, 0, it's right here. We're going to move that up 1. 6, -1 moves to 6, 0. And 9, -2 moves to 9, -1. So again, the shape is not changing. We are changing the location. So the most important part is recognizing what parent function you're dealing with and then knowing your transformations. Okay, so 25, because we're almost done, is a piecewise function. Now the way I teach these, I teach it as doing table of values. So for x's that are less than or equal to 0, that's this first row, you're going to use the graph x squared plus 3. For x's that are greater than 0, you're going to use the graph 3x minus 1. So you're going to pick your x and y chart based off of those domain restrictions. This says x's need to be less than or equal to 0. So 0, -1, -2. You plug those in. So 0 squared plus 3 is 3. -1 squared is 1 plus 3 is 4. -2 squared is 4 plus 3 is 7. And then you do want to note whether or not this endpoint is opened or closed, and that is a closed circle because it has the equal to. Now I know this says greater than 0, and most people are like, okay, then we don't use 0. You actually do still use 0, you just realize that it's not a closed circle in this case, it is open because it does not have the equal to. There's still graph very close to 0, so we don't want to lose any of our graph that's getting close to 0. We're just not equal to 0 on this part. So we plug these in, so that'd be -1, and 3 minus 1 would be 2, and 6 minus 1 would be 5. Once you have your table information, you're going to plot them. Okay, so 0, 3, and that's a closed circle. -1, 4, and that's just a dot. That is not opened or closed, really considered. It's not an endpoint, it's just a dot. And then -2, 7. So 1, 2, 3, 4, 5, 6, 7. Okay, this is an x squared, so notice this has that parabola shape to it. Okay, and it does go on forever because this says less than or equal to 0, which means this pattern continues forever that direction. 0, -1 is an open circle. Every other point we plot is just a point. So 1, 2, 2, 5. And this is just mx plus b, so this is a straight line. Well, that is not a straight line that I just drew. Straightish line. So that's my piecewise function. It's a graph that is broke up into pieces based on a domain restriction, and different functions apply to different domains. Same thing for 26, except we have 3 pieces to work out. So for x's that are less than or equal to -1, we're going to be using 2x minus 3. For -1 to 3, we're going to be using x squared. And 5, x greater than 3. Let's write that first, be consistent. Our function is just 5. So think of these as y equals, y equals, y equals. I didn't write that on the last one. So less than or equal to -1, we do need our endpoint, so -1 and then less than or equal to that. So -2, -3, noting that this is closed because of the equal to. So -1 would be -2 minus 3, that's -5. -4 minus 3 is -7, and then -6 minus 3 is -9. On this one, be very careful because there's 2 endpoints. You need to plot -1, you need to plot 0, 1, 2. I usually just do all the points in between. This endpoint is open because it does not have the equal to, and this endpoint is closed. Okay, so if we square these, this would be 1, 0, 1, 4, and 9. And then y equals 5. So for x's that are greater than 3, that means you do include 3. You just note that it is open. And then it's 4, 5. So this is just anything you plug in is a 5 because there is no x to plug in. So this would be -1, -5. So that is a closed circle. -2, -7, just a point. And -3, -9. So notice this is sloping down this direction. -1, 1 is an open circle. 0, 0 is just a point. 1, 1 is just a point. 2, 4 is a point. 3, 5, 6, 9 is a closed circle, and it is the endpoint. So notice this is part of a parabola. And then at 3, 5, which is 1, 2, 3, up 1, 2, 3, 4, 5, we have an open circle, and then this is also the same height forever. So it's just going to be a horizontal line. Okay. And then this last example for the review for 2A. Use the graphs below to identify the x-intercepts, the y-intercepts, and state whether the graph has x-axis, y-axis, origin, or none of those symmetries. Okay, so the x-intercept here is -4, 0, and 4, 0. So those are my x-intercepts. My y-intercept is 0, -4. And if you fold this across the y-axis, it matches up. So this one has y-axis symmetry. Okay, this one has, it looks like an x-intercept of -3, 0. That one's kind of off kilter here. That would probably be 5, my guess would be. And then this is, well, this is easy to get. This is -3 to 5. So that is a distance of 8. So that would be halfway between there would be 4. So that's going to be at 1 for that vertex. But we don't need that. We need the y-intercept. Sorry. I was thinking about the vertex. So yeah, the y-intercept is -15. So for this, Notice that even if you fold this, yes, there's symmetry, but it's not on the actual y-axis. There's no x-axis symmetry. It doesn't fold down and match. Origin means folding twice and matching. So fold over the x-axis and fold over the y-axis. And if we do that, it doesn't match. So this one would have none of those. Okay, for this one right here, it looks like our intercepts are 0, 2, and 0, -2. Those are both y-intercepts. And it has an x-intercept of 4, 0. And this one has what we call x-axis symmetry. It folds over the x-axis nicely and matches itself. And then this one has just one intercept. It's 0, 0, but it is both an x-intercept and a y-intercept. That's the only time you can be both. And then this folds twice. If you fold it across, it would be up here, and if you fold it down, it would match here. So that is that origin symmetry. And that's it for this video.